Alrighty, so today's lecture we're going to continue discussing basic DC circuits. We've gone over Ohm's law and of course resistors in series or parallel. And what I'd like to do today is cover kind of an implication that comes from Ohm's law. It's nothing more than just a quick little shortcut type calculation. So it's not some big formula or anything. It's just a way of seeing how to do something a little quicker than maybe you would normally. And that's called the voltage divider. So the way it works is this. Let's say we have a circuit composed of some resistors in series. Let's say we have 3 resistors. And this is the voltage source. Let's call this R1, R2, and R3. And what we've seen so far using Ohm's law is, let's say maybe we want to know what is the voltage dropped by resistor 2. So we know, of course, current will be set up in this circuit. The electrons are moving around. And as the current flows through these resistors, those resistors drop the voltage. That is to say, you could think of it kind of like using up some of the power. Now, I'm using the word power here not in the true sense of the power in a circuit, but just common terminology, common language type stuff. There's a certain amount of voltage trying to push these electrons, trying to push the current through the circuit. Now, again, we will see as we progress further, this kind of image, this view we have in our minds, isn't quite accurate. There's a lot more complication going on. But for now, there's nothing wrong with just imagining this is maybe something like pipes with water flowing through it. And a battery or your voltage source is kind of like a pump pushing the water molecules through your pipes, whatever. These resistors, as the current is flowing through them, is kind of like using up some of that voltage. We call it dropping the voltage. And so one thing we know, or one thing we will find out using the next kind of technique, which is Kirchhoff's laws, is that if you have a certain amount of voltage in your circuit, that voltage has to be used up by the time the current comes back to its starting location. So if this particular battery here supplies a voltage of 12 volts, then all 12 volts will have to be used up. And the way we could see that this is true is we could use Ohm's law, for instance, and we could say, well, I, the amount of current that flows through the circuit, is V over R, where this is the voltage of the source and the total resistance of the circuit. This will give us the total current flowing through the circuit. And so, if I wanted to know how much voltage is dropped by R2, the first thing I need to know is how much current flows through R2. And so, I know the voltage from the source. That's easy. That's just a number. The total resistance, however, I have to calculate it. And indeed, for this particular example, R total, being that they're all 3 in series, is just R1 plus R2 plus R3. So now we have that total resistance, whatever this number happens to be. And now I could say, well, what's the voltage dropped simply by R2? Obviously, R1 is going to drop some voltage. R3 is going to drop some voltage. But I don't care about those. All I care about is how much voltage is dropped by R2. So, first thing I would do is find the total current running through the circuit using this equation here. This goes in for the total resistance right there. I have the total voltage over the total resistance, gives me the total current. Then I would say the voltage dropped by resistor 2 is going to be the current. Let me put it in line. The current coming into resistor 2, where in this particular circuit, because it's all series, it's just the total current running through the circuit, times the resistance of R2. Right? So this is just I total for this particular example. This isn't always true. If these are parallel resistors, then the current that flows through R2 is not the total current, but only the amount of current that goes to that particular branch and so on. But for this one, it's the total current times R2. And the total current, of course, is V of the source, the total current, or the total voltage, I'm sorry, divided by the total resistance, R1 plus R2 plus R3. And all of this is multiplied by R2. Right? So all I did was I said, this is the equation for the total current. Plug it in right there, it becomes this. So that times R2 is this. And now we have, if I rearrange it just a little bit, now we have the equation for the voltage divider. It says that the voltage that would be dropped by this particular resistor that's in series with the other ones is given by the total voltage of the circuit times the resistance of resistor 2 over the total resistance, R1 plus R2 plus R3. And this is called the voltage divider. This is kind of a shortcut. Instead of doing these two steps, number one, calculate the total current, then number two, plugging into the equation to get this, we could just go straight to this. And this is generally true. If you have a series of resistors connected in series specifically, and you want to know how much of the voltage is dropped by a particular resistor in that series, well, you take the ratio of the resistance of the resistor you're talking about, or you're trying to calculate, divided by all the resistors that are in series, added together, the total resistance, and you multiply that ratio by the total voltage. So this is kind of like saying, well, resistor 2 is 2/3 of the total resistance of the circuit. So how much voltage is it going to drop? It's going to drop 2/3 of the total voltage. Very, very easy concept. Let's see it in action. Here's an example. And we'll do the example I just did, but with actual numbers. We have a battery connected with a number of resistors. Let's say the battery has 10 volts. This is 2 ohms, this is 5 ohms, and this is 3 ohms. And the question is, what is the voltage dropped by the 5 ohm resistor? Okay. The voltage divider says, well, all of these resistors are in series, so I could do the voltage divider. And so the voltage dropped by the 5 ohm resistor is going to be the total voltage, 10, times the resistor I care about, the 5, divided by the total resistance, which is 2 plus 5 plus 3, which is 10. And this gives me a voltage drop of 5 volts. So of the 10 volts supplied to the circuit, 5 of those volts is used up by the second resistor. And of course, like I said, as we'll see by a technique we get in the future, Kirchhoff's laws, or one of his laws, the other two resistors must drop the rest of the voltage. This one dropped 5, so there's 5 more to go. The 2 is going to drop some, the 3 is going to drop some. Okay. Now let's verify that this is actually true. Let's do it the way we normally would if we don't know the voltage divider. So if we don't know the voltage divider, what we would say is, if I want to know how much voltage is dropped by the 5, well, I need to know the current that runs through the 5 times the resistance of the resistor 5. Okay? Basic Ohm's law. Well, first thing I need is what is the current that's running through this particular resistor. Well, generally what I do when I do normal Ohm's law stuff, even if I don't really know what it is specifically I'm trying to calculate, usually it's a good idea to just calculate the total current in your circuit. So let's try it. In order to get the total current, I need the total voltage and the total resistance. The total voltage is easy, that's 10. So now I just need to calculate the total resistance. Well, these resistors, the total resistance here, are in series, so all I have to do is 2 plus 5 plus 3, which is a total resistance of 10 ohms. I now know the total resistance, so now I could say V equals IR for the whole circuit tells me I is V over R. So that's 10 volts for the whole circuit over the total resistance of 10. That means the total current is 1 amp. Now I know the total current. Okay, now let's go back and think about the problem I'm trying to solve. I'm trying to figure out, because I want the voltage dropped by the 5, I need the current that runs through the 5. Well, here we have just resistors in series. That means this current has nowhere to go except straight through all the resistors. There's no option, there's no different paths it can take, so it has to go through here. So that means whatever this total current is, that's the current that goes through each one of these resistors. It's got no choice but to do that. So I now know the total current of 1 amp happens to be the current that goes through the 5 ohm resistor. Okay, so that's 1. And then what I need is the resistance of resistor 5, the one I'm looking at. Well, that's easy. That's 5. So the voltage dropped by the 5 ohm resistor is the current that runs through it, which in this case is 1, times its resistance, which is 5. So I get a total voltage drop of 5 volts. And indeed, that matches. As it should. That's the whole point. All we did, this isn't something new, this isn't some fancy pants equation someone invented. All they did was say, this is how we generally solve it. We want the total current, so we want the total voltage over the total resistance. Calculate the total resistance. The voltage divider works when these are all series. So I add up all the resistors together, so I get a total current that looks like this. I multiply that times the resistor I care about, and things get moved around, get rearranged so that it looks like this. And this is a general technique you could use now. Given a circuit with some number of resistors in series, if you want to know the voltage drop by one of those resistors, just take the ratio of its resistance to the total resistance and multiply that by the total voltage. That's what we did here. Notice, by the way, how much faster it is to do it with the voltage divider than to go through all of these steps to do exactly the same thing. The green is how we would do it using Ohm's law if we don't think about it as a voltage divider. And the black up there on the top right is, now that we know about this voltage divider thing, let's just kind of skip a step and go straight to the answer. We know how to do this. It's all still V equals IR and all of that stuff. But this kind of makes some intuitive sense. You have a number of resistors. Some are bigger, some are smaller. The bigger resistors use up more voltage. Or another way of saying it is, it takes more voltage to push the current through these resistors, so it uses it up. So if you have a resistor and you want to know, well, how much voltage is this going to use up of the total voltage supplied? Well, it's equivalent, or at least it's proportional to, how much of the total resistance is this resistor. If this resistor is half of the total resistance, then it's going to drop half of the total voltage. If it's a quarter of the resistance, then it's going to drop a quarter of the voltage. Very, very nice little bitty method here, but it's pretty interesting. And it kind of helps you take away a little bit of the pure mathematical recipe stuff and start thinking logically and intuitively about what we're doing here. Now, before I end it, I do want to say there is something else called the current divider, which is not quite as prevalent and not as popular. But it is true, so it can be used, but you just have to be careful. Let's say you have two resistors, and these resistors are in parallel. Okay, so we have R1 and R2. And some voltage is being applied. And maybe what we'd like to know is how much of the current runs through R1. So we know there's some total current coming in. That total current, when it hits this node here, it's got two branches it can go through. So some of the current goes this way, some of the current goes that way. Now we know from intuition, we've heard in electricity follows the path of least resistance, which is not technically true, though it has some amount of truth to it. It doesn't say that if R1 is smaller than R2, then all of the current goes through R1. No. There's always going to be some current running through both branches. It's just that more current will run through the smaller resistor because it's easier to go through. Why would the current try to take the path that's harder to get to if there's another path that's really easy to get through? Some of the current will take the harder path just because it's got no choice. The current's being pushed through. It's just a smaller opening, so it's harder to get through. So less current flows that way. The other one, the one with the smaller resistor, is like a big, huge pipe. So there's a lot of space for the current to flow through that. So if I want to know, okay, given a total amount of current coming in, how much current will go through branch 1 versus branch 2? Very similar to the voltage divider thing. We've got 3 resistors. Each one is going to drop some amount of voltage. How much is dropped by this particular resistor? Here, current's coming in. The current's going to split. Some will go through each path. How much goes through resistor 1 versus resistor 2? And this is called the current divider. And it looks very, very similar. It says that the current that goes through the R1 is going to be equal to the total current that's coming in times the ratio. Now here's where it differs. Instead of it being the ratio of R1 to R total, now it's the ratio of R2 to R total. Okay? And by the way, this R total is not like you're adding them in parallel. This is R1 plus R2. Here. Okay, so the total current, we've got a 5 ohm and a 6 ohm. Well, the 6 ohm is harder to get through, so more should be going through the R1. But notice the big difference here. For the voltage divider, if we want to know how much voltage is dropped by R2, the ratio is R2 to R total. But for a current divider, if I want how much current goes through I1, that's not R1 over R1 plus R2. It's R2 over R1 plus R2. So like the other side. If we want the current that flows through R1, we do the ratio of R2. Okay, so it's the opposite. Which makes sense because now we're talking about parallel stuff rather than series stuff. So it doesn't have to be the same. But the same basic logic holds here. If you go through and you do the calculations with this, it'll make sense. If you want to know how much current is split or divided among the branches, this branch is going to get a certain amount. That branch is going to get a certain amount. If you add them together, that's the total current. So how much goes through branch 1? Well, it's branch 2 over the total times the total current. And vice versa. If you want to know how much current goes through R2, then it's R1 over R1 plus R2 times the total. Okay? This, though, is not quite as important because it just doesn't come up that much. I believe also it only works if you only have 2 resistors. It doesn't work if you try to do more. I'm not very sure about that just because I rarely ever use it. Almost everybody uses voltage divider. This comes up all the time. So this is the one you really want to know, but just know this also works. There is kind of an equivalence here, something similar between the two. Very similar look. Voltage, how much is dropped by resistor 3? Well, it's resistor 3 over total resistance times the total voltage. For the current, It's vice versa. You want to know how much is dropped by resistor 2, then it's R1 over R1 plus R2 times the total current. Anyway, I just wanted to show you this little technique because it may help you do some calculations a little faster. You don't have to do voltage divider, or at least you don't have to think of it like you're doing voltage divider. You could just do like I did here. This part down here is how we would have done it before we learned about voltage divider. It's just that we take the result from what we do there, and we just do a little shortcut. We say, okay, let's start with the end. We know what we're getting to, so let's just start there. Why go through all these mid steps? So it's just a time saver. Anyway, hope this is helpful. Of course, it may be wise to go back and look at some of the example problems or practice problems that are posted on Canvas, and any that have just series resistors in it. Try solving them using voltage divider and see if you get the same answer. You should, of course. If not, then go back and see, what am I doing wrong? Am I not adding the resistors correctly, or whatever it is? But it really should work out pretty straightforward. Anyway, if you have any questions, let me know, and I will see you next time.